introduction. This is Vickenty, and he's going to do an interesting talk about Perl and Rust and how they talk to each other via FFI. So enjoy.
Hello. My name is Vickenty, and I'm going to talk about FFI, Rust, and Perl. So, what is FFI? FFI is a foreign function interface, and basically, in broad terms, a way for two languages to talk to each other. It's a feature of one language to talk to another. For example, Perl has a module called FFI. You can load a C library with it, you can call functions in it, and you get a C-level interface out of it. What Perl also has are extensions. They integrate with the interpreter a lot tighter, so they have to be written specifically for Perl, but then you can manipulate Perl data types directly. So, for example, all data serialization libraries for Perl are written as extensions, so they can be fast and they can do what they need to do with the values directly. And of course, Perl is written in C, so extensions are also written in C. And what they actually are when you build them, they are basically a specially crafted dynamic shared library that Perl can talk to. This library has to follow several conventions that Perl expects it to, and these conventions are called binary interface, application binary interface. So it's basically a set of functions and global static variables that are available to the extension and that Perl expects from the extension. So Perl expects a well-defined name for a special initialization function that you have to provide, and then provide you API to call to manipulate values from the interpreter and do all this stuff. So Rust has FFI. It can build a C library. So in theory, at least, we can make an extension for Perl in Rust. This is well-documented stuff, so I'm not going to stop it here for too long, but basically what we have, we can annotate certain functions as having extern C, so they become like C functions, and we can put no mangle on them, so they have controlled name, otherwise Rust will put junk in there. And we can also import functions by putting declaration without body inside an extern C block. So then we put a special crate type in the cargo toml, and we have a shared library. So the problem is Perl doesn't have a stable binary interface, so we don't know what functions we're going to need. We don't know what signatures they use. Types change between versions, and it even changes between different builds of the same version of the interpreter. It has a lot of knobs to tune, and of course people do that. What it has is a stable API, otherwise it would be impossible to write modules for it. It's a C program, so it provides a C header file with a bunch of type aliases that abstract away changing types, providing them with the stable names you can write. And it also has a bunch of C macros to hide certain varying aspects of the binary interface. So if we want to do an extension in Rust, we need to get first the binary interface implemented in Rust. Rust bind again nowadays can handle most of that difficult job. It will read a header file, find all the function declarations, and write matching Rust declarations for them. So it will translate type aliases, it will translate constants, static variables, and function declarations as they are in C at the function level. That didn't work very well when I first started this project about 2 years ago. It would crash with a segfault. So instead I wrote a small Perl script that does basically the same thing, except it doesn't read header files. That would be terrible. Fortunately, Perl has a spatial file in its source distribution that lists all the functions and all their signatures, and there is additional information that can be used to generate these bindings from that file. So I extracted this file for every version I support and bundle it with the crate. So then at build time, we can build bindings for the specific version of Perl, for the specific variant of Perl, the way they should be, and match the interface. So once we start doing that, we notice that things are really different. So one of the big features in Perl, there is thread support. It's optional. So when you build Perl with threads, you get an extra parameter stuck into every function. It's not present when you build without threads, and basically every API endpoint it provides is actually a macro that secretly passes this extra parameter when necessary. So, of course, it will be very inconvenient if our Rust code had to deal with this directly. So, what do? We basically turn it inside out. We always provide a context parameter. Rust has kind of objects, so we use that. When there is no pointer to pass, it's just an empty type, for historic reasons mostly. And when we have a pointer, we do have a pointer, and we pass it in. This code is also generated from the raw bindings by the Perl script, so there are no macros anywhere. It's just generated to match the exact version that we use. Another problem, a good chunk of API is just macros. There are no functions that can be called, so they don't exist at runtime. They exist only in source form. They usually implement hardcode paths that are inlined for performance reasons. And things like getting a value out of a runtime object, like reading an integer from a variable, for example. This is a macro. And what it would do, it would check a flag and maybe return a field from the struct directly, so you get the whole quick path, or call a conversion function if a conversion is necessary. All this is super unstable. This is the part that changes between versions often because it's hot code and it's being worked on and optimized. And these structs are private. They are not part of the documented API, so even if we had Rust bind and do the translation for us, we can't really write Rust code to access them because we don't know what's in there. Things may get renamed or moved around, and the value of flags, all the invariants that need to be maintained are really, really private. So what we can do, we can put each macro into its own C function. We can then compile this C source alongside our module. Again, we get because we compile it for the specific version of Perl, we get all the implementation correctly, and then we call these functions instead. It's a bit slower because there is no inlining, and there is a bigger problem hidden here. But
can't you annotate this with flags to make it inline?
No, because it's in C. So Rust cannot inline C code. Actually, it can, but it's really hacky, terrible thing. And all this always work. We need to do just to get to what C already can do. So to catch up to C level, we had to terrible stuff. On top of this, we can actually build improvements. We can try to maintain safety of the API, because in C there are a lot of invariants that the programmer has to maintain manually to think about them. Maybe we can help with that, and of course we can implement conveniences on top of conveniences that Rust normally provides, like iterators, automated reference counting through drop, and move semantic. And they can, of course, use type inference. So, to give you an example of how it ended up in the end, here is a piece of C code. It's not really C because it's especially pre-processed C. That basically computes a sum of elements of an array. It iterates through the array, gets each element one by one, checks if it's defined, and then adds it to the accumulator. So you see there is some low-level stuff we need to do. There is mortal, terrible thing.
Is this generated code? Or is this
No, this is like handcrafted code. Okay. It's just then pre-processed into normal C, and then it is compiled to a module.
So is the init column macro then as well?
It's kind of section for the preprocessor. It's not a C macro. It's they have a special kind of syntax invented for this.
I see.
It's a go-to label in C, isn't it?
Yeah.
It's just a go-to label. You can jump to it.
Yes, except it's not really a go-to line because there is nothing jumping to it. Yeah, but it looks like one, definitely. And there are no braces. You get an array, you iterate, you map, you sum. That's it. But this doesn't really, only looks nice.
Wait, what is XS?
XS?
It's a beginning.
XS is what Perl calls its extension API. And,
so that's a macro implement.
and this is just a normal, a regular macro, like macro 1.0, that just gets a bunch of tokens and generates Rust functions that have the low-level API that Perl expects.
And what's the NV type?
NV is a numeric value, just a floating point. Depending on how you build.
So this is like a
It's
type that's mapped to Perl? Or?
It's an alias for F64, but depending on how you build Perl, it may be F32 as well.
Mm-hmm.
So.
But that depends on how you're mapping it back to Perl? Or?
This is what Perl calls its floating point type.
Right.
And depending on how you build it, it can be different, like a float or double. Then we need to use the same thing to talk back to Perl. So this is why we're not using F64, otherwise we need a cast. And this way we just directly do what Perl expects us to do. So let's see how we can add safety to this. Perl is not a garbage collected language, it uses reference counting, and the problem is it doesn't use it consistently throughout. It often does what in Rust terms we can say borrowing. When there is a value in the array, you fetch it. It doesn't add one to the reference count, it just gives you the pointer directly. If you mess with the array in between, it can easily invalidate your pointer and you have problems. But they do it on purpose. There is a good reason to do this, and the reason is to avoid a lot of short-lived reference counting bumps, and increments and decrements all the time when you try to do something like this. It's actually safe if you don't mess with the array to keep this pointer untracked as long as you use it immediately after you receive it. So we can do something like this in Rust. Basically, we need to guarantee that whatever happens to the pointer after we get it from the array, we immediately consume it one way or another. We bump reference counting or we convert it to something, but we never give the user pointer that is not guaranteed to live long enough. We can do this with a trait that gets the raw pointer and then does something to it. The invariant there is that it will either bump the reference count or consume it, or consume the value without exposing this potentially dangling pointer to the user. Then, when we implement array fetch, we can use the trick from the standard library by bounding the return type, so the user can tell us what action they want to happen. They can say convert it to F64, or they can say bump the reference counting. We then dispatch to the correct implementation of the trait, for example, like this, and we get the correct behavior, and we don't do any unnecessary reference counting. This worked well, but this didn't work very well for strings. Runtime values can contain strings. They have them in just character bytes, character arrays inside. And those are not reference counted. And because everything is shared in Perl, so you can have multiple references to the same string, any piece of code anywhere can modify it. So when you get the pointer, you have to do something with it immediately, but you cannot protect yourself from it being modified. If you call anything, if you dispatch to anywhere in the code, and it can be very subtle because everything is overloadable in Perl as well. So as much as getting next element from an array can trigger some weird behavior and invalidate your pointer. And this isn't really, there isn't really a way to contain this, because we cannot prevent user from doing, we cannot give them a string reference, for example, or a slice, because that means it has to live and not being modified as long as the slice is alive, but we cannot guarantee that. And we cannot use the trait trick because there is no clear defined set of actions that we can make with a string. We would need a lot of different implementations, right? So the only thing we can do that is copy, and it's kind of worse than what C can do, but safe. And the worst thing that happened to this project was exception handling. So Perl has exceptions, of course, and as long as the extensions are concerned, they work pretty much like panics. You can handle them, but you can have cleanups but you cannot really intercept, catch them, or handle them in any other way. So Perl implements exceptions as set jump long jump pair. Who knows what this does? So it's basically a worst kind of pair of C functions. First you call set jump it initializes the jump buffer, and then it returns 0. So you can then pass this jump buffer down the stack to some other function, and when in the end you call long jump, it never returns. Instead, set jump returns again with a different return value. So this piece of code prints died and not success. And this is kind of a problem because whatever happened between the long jump and send jump is forgotten and ignored. So let's see, we have a piece of Rust code which Perl code calls. We have some values on stack that have a destructor, so we need to run cleanups in the end. And then we make some calls to the API, so that this kind of worked. In the end, and then some exception happens. So it will call long jump, it will jump to some exception handling code inside the interpreter, way past our stack, and any cleanups that we have will not run because it doesn't know about them. So what we need to do, we need to insert guards on both sides. On the right hand side, we basically put a try-catch block around every API call. So we catch exceptions, we convert them into panics, so then we propagate them through the Rust stack. They do all the stack unwinding, call all the destructors, drop implementations and such. And then when we reach the FFI boundary again before returning into Perl, we catch this panic, we extract the original exception information, and we resume a Perl handling of the exception. This is slow. So the piece of code I showed before is about 4 times slower than pure C implementation because it basically does pretty much nothing but call API. It calls API to get a value out of the array, it calls API to get a value out of the array element. And it's still faster than Perl, but not that much faster, but safe. Yeah, so to conclude, it takes a lot of work to get to where C started, basically. It's long preparation. It's not really trivial to do the same thing that C does, even though Rust supposedly can do these things. Well, it can, but it's not trivial. And not all unsafety can be efficiently avoided. So you cannot really encapsulate around certain aspects of unsafe code without making it much slower. Yes, that's it. Thank you. So if you have any questions?
So you're working for Booking, I assume?
Yes.
So what was the original driver for this project?
Pretty much curiosity. It was when Rust first came out at 1.0, a couple of projects started, Ruru for Ruby and Neon for Node.js, and I was curious how it actually can be made. Maybe it will work, maybe it wouldn't. I think it didn't quite work very well, but it was an interesting and I learned a lot, so it was pretty much dictated by curiosity.
So it's not in use now?
No.
But would it be possible to adjust the Perl side of the FFI so that you get more efficient, like providing explicit handlers for exceptions?
Maybe. I don't think exception handling can be improved that much. What can tip the balance here is because these the problem is that macros actually don't need this exception handling in most cases. They don't dispatch the code that can throw an exception. So by avoiding this try-catch in more situations, you can be faster. But when it dies, you really need to do something about it. So either Rust exception system becomes more pluggable, and we can use what Perl does, because it has API for destructors, it has API for cleanups. It's pretty sophisticated. So if Rust could, for example, schedule in the local specially marked function destructors in a different way than it normally does, then we would avoid this unnecessary work of trapping the exceptions. But unfortunately, it's, I don't think, even in the plans.
But if you don't interact with Perl while you're running the Rust code, would you be okay then? If you just like keep it only Rust and then return something back to Perl?
Yeah, if you, depending on how much API you actually call, it may be easier to, it may be much faster. For example, if you, I don't compute hashes or something. But then it might be easier to just make a C library and call it through the FFI interface I mentioned in the beginning. Then you don't need all this complex machinery and Perl scripts and build problems that it brings.
But given so many disadvantages, do you see any advantages of using this?
I don't. So it really depends. I wouldn't recommend because the build process at the moment is kind of convoluted. It's basically was abandoned a while ago, so I'm not sure it's good to use.
But I guess I know for example for Mercurial, which is implemented in Python, is now developing a Rust interface. I mean it's just a call layer so that you have a faster command line interface. And if you check, for example, with the state of a repository.
So what I think Mercurial is trying to do, they porting more or less to Rust, but in an incremental way. It's a bit easier if you just call Perl, for example. If you call a function and then you expect to run it for a long time, exception handling might not be a problem. And I think Python implements exceptions slightly differently, so they don't really use set jump, long jump, they just return. And that's much cheaper to integrate with. So that's something specific to Perl, I think.
It's much more natural.
But I think what's interesting about the Mercurial project is that they have a wrapper in Rust, so they actually run their Python code from Rust rather than doing it the other way around. May provide some advantages.
Yeah, so the advantages they get, they can port it piece by piece, basically. So that's the advantage they get, but I'm not sure about how much advantage they get from the integration with Python otherwise.
But could you do the same? So you say you have a Rust program which embeds a Perl integrator for...
Yeah, that you could do.
Okay.
Definitely.
But then it still wouldn't solve the exception problem.
No.
Maybe.
It may not be that much of a problem then. If you just call a big function like main and it runs for a long time, you don't communicate between the two, then it's actually not that big of a problem. It's still faster than Perl, but not that much faster. So
that's actually my experience with Node.js. That you just if you're using like this for like performance, you would call your Rust function with like all your data and then process all your data at the same time, like batch everything, and then just return it. So avoid like
Crossing the FFI boundary.
yeah, as much as possible.
okay, thank you.